Okay, during this hour or so, we will just do some problems related to Laplace transforms, inverse Laplace transforms, and also some simple examples on calculating the transfer functions. Okay, so let us start by finding Laplace transform of a signal which looks like this, say in time domain is sine square t over t plus t e power minus a t sine of a t. And during the computation of this, we will use lots of properties of Laplace transforms which we learned earlier, right. So, this is a combination of two signals f1 of t and f2 of t, right, and using the linearity property, the Laplace transform of f of t can be individually computed as the Laplace transform of f of t plus the Laplace transform of f1 of t and f2 of t. Okay. So, let us start with this thing first, finding of Laplace transform of sine square t. Okay. So, okay, do not worry where the t has disappeared, I will tell you a magic of how to take care of that t. So, this would be sine square t can equally be written as 1 minus cos of 2t over 2. Okay. Here I can further use the linearity property. This would be Laplace transform of 1 over 2 minus the Laplace transform of cos 2t over 2. Okay. Now, I just recorrect the formulas. So, this would be 1 over 2s minus 1 over 2 cos 2t would be s over s square plus 4, right. Okay. My original signal is of the form sine square t by t, right. So, I need to find the Laplace transform of sine square t over t. Okay. So, so far I have found what is the Laplace transform of sine square t. Okay. Is there any property which helps me in finding the Laplace transform when I just divide a signal by t, right. So, just recollect the frequency integration property. Okay. So, what does the frequency integration property tell me is that if I have a signal in time domain x of t 1 over t, then this Laplace would look something like this, s to infinity x of u d of u. Okay. And therefore, the Laplace transform of sine square t over t, given that the Laplace transform of sine square t is this, I just use the frequency integration formula, this would become 1 over 2 integral of s to infinity, and using this formula should be 1 over u, so minus u over u square plus 4 du, right. So, so what would this be? It would be half of u minus half log of u square plus 4, and everything going from s to infinity. So, this simplified would look something like this: 1 over 4 of s square plus 4 over s square. Okay. So, this is the Laplace transform of sin square t over t. Okay. So, next we need to compute the Laplace transform of the second signal, this guy. Laplace transform of t e power minus a t sin of t. Okay. Now, I use equivalently the frequency differentiation formula, sorry, sin of a t. Now, I just use the frequency differentiation formula here. Okay. What does the formula say? That t x t, the Laplace of this would be minus d over ds x of s, right. So, here I have t multiplied by this signal. Okay. So, this would be minus d over ds, the Laplace transform of this guy, e power minus a t sin of a t. Okay. Now, next I use the frequency shifting formula, right, multiplying by e power minus a t. So, this would be minus d over ds, the Laplace transform of sin of a t, this. Okay. So, this would be, now I know the Laplace transform of sin of a t, d over ds over, so Laplace transform of sin of a t would be a over s square plus a square. Frequency shifting would give me s replaced by s plus a square. Okay. And that d over ds of a over, sorry, s plus a whole square plus a square would be twice a over s plus a square plus a square the whole square, right. And therefore, the Laplace transform of our signal f of t is a combination of sin square t over t plus t e power minus a t sin of a t would be just this one, right. The first guy was this one over here, one over 4 log of s square plus 4 by s square plus okay. So, this will be a s plus a here, right. If I differentiate the denominator, I will have 2a and s plus a plus twice a s plus a over s plus a whole square plus s. Okay. So, this just illustrates that you are using the frequency integration, the frequency differentiation, frequency shifting, and of course, the linearity property, right. Okay. So, next if I have a signal, okay, let us see f of t looks something like this, right. It is 1 for t between 0 and 2, it is -1 for t between 0 and 4, together with the property that f of t plus 4 is f of t. It is like a periodic signal with a period of 4. So, I can just plot this signal, right. So, this is f has a value of 1 from t going from 0 to 2. So, it will look something like this, right, and at 2 it takes a value of -1. So, this until it reaches 4 and keeps on doing this, right. So, this I have a 6 here and 8 and so on. Okay. Okay. Now, this is a periodic function. Okay. So, what is the Laplace transform for a periodic function? L of a given function f of t is 1 over 1 minus e power minus ps integral 0, just integrate till the time period p e power minus st f of t dt, right, or this guy p is the time period. Okay, which in our case is 4. So, this would simply now translates to 1 over 1 minus e power minus 4s, and this signal from 0 to 4 has two components, from 0 to 2 this component and from 2 to 4 this component. So, I will integrate each individually, 0 to 2 e power minus st dt plus 2 to 4, it is a -1 there, so this will be minus e power minus st dt. Okay. Then I just skip all the computations. This is a very straightforward integration which you learn very early in your high school. So, this would simply be 1 minus e power minus 2s over s 1 plus e power minus 2s. Okay. This is quite straightforward, right. Once you just plug in this formula, these are easy to compute. So, next we will look at solving non-homogeneous differential equations. Or also called force differential equations. So, it just looks like this, say y dot or say y prime plus y is some sign of t with the initial condition y of 0 being 1. Okay. Now, I take the Laplace transform on both sides. So, I have s times y of s with this initial condition y of 0, okay, plus y of s. On the right hand side I have sin of t, the Laplace transform of sin of t is 1 over s plus 1. Okay. Okay. So, I substitute s plus 1 times y of s, y of 0 is 1. So, it is 1 over s square plus 1 plus 1. I will just take this guy here, and this would give me y of s is s square plus 2 over s plus 1 s square plus 1, right, just rearranging terms. Okay. So, I can rewrite this as 3 over 2 1 over s plus 1 plus 1 over 2 square plus 1 minus 1 over 2 s square plus 1. And this is just by applying the method of partial fractions or solving this kind of equations. Now, y of t would simply be the inverse Laplace of y of s. Okay. So, the first inverse of s plus 1 would be e power minus t plus, well, this inverse is just a sinusoidal signal sine of t, and the last one is s over s square plus 1 is cos of t, right. Okay. As simple as that. So, just this step here is a crucial one of identifying these numbers here and to write this in terms of fractions. Okay. So, next we will look at deriving transfer functions from given simple circuit models. Okay. So, let us say I have a circuit with the input voltage V I, R here. So, I will call this as R1, the capacitor C1, L1, this would be C2, and this is R2. Okay. So, I need to find what is, so all initial conditions are 0, right, that is the assumptions I will make. Right. Okay. The first is find the transfer function. So, if this is capacitor C1, let me call this voltage as Vc1. Find the transfer function Vc1 of s over Vi of s. Okay. So, let us step by step follow what we had learnt earlier, how to determine my transfer function. So, first is, well, write down the equations, right. Or the differential equations which model my system. Okay. So, let me call this current as I1 as I would do it in any circuit analysis, and I2. Okay. So, the first equation for loop 1 would look like this, right. So, that V1 is I1 R1 plus 1 over C, so I have I1 minus I2 plus I have this guy L1 dI1 by dt. Yeah, sorry, 1 over C integration. Okay. So, there is also another way of doing this. Now, since we are used to writing things in linear equations, I will just write this entire circuit in Laplace representation, right. So, okay, I will just try to draw this here. This a capacitor here, a Vi, this guy, an inductance here, capacitance R2, this is C2, this is my C1, L1 and R1. Okay. So, in the Laplacian domain I could write this as SL1, capacitor I could rewrite as 1 over S times C1, this guy would equivalently become 1 over S times C2, right, and this would be I1 of S, the current in this loop, and the current in this loop would be I2 of S. Okay. So, okay, let us go back here, and if I were to write these equations in the Laplace domain, so that will be I1 of S R1S plus, it just be R1, right, there will be no S here, so it will be the same. This would be I1 of S minus I2 of S plus S L1 I1 of S, right. So, I can even write it directly from here, right. So, I have V1 is I1 R1. I can directly, I do not even now need to bother about writing the integral equation, but I have 1 over S C1. I can just look upon this now as a linear element, 1 over S C1, the current flowing through this is I1 minus I2 plus the current here I1 times SL1, right. So, I can just write down the equations without even going through this step, if I can transform from this circuit to something like this, right. Okay. And for the loop 2, okay, so loop 2 I have VC1 equal to, so I will just use this circuit now. So, this is my VC1 here, VC1 of S, maybe with a convention like this. Okay. VC1 is current through here is I2 times SC2 plus R2, okay, all this will be in S, R2 I2 of S. Okay. Now, I have equation 1, I have equation 2. Okay. So, now what do I need to find? I need to find out VC1 by V1. Okay. So, just take this one, right. The voltage across this capacitor VC1 is also, well, what is this, right, this voltage, if I look at this equation here, well, it is just simply this one, right, here, this one or this one. This is 1 over Cs I1 of S minus I2 of S. Okay. Let me call this as equation number 3. Okay. So, what do I need to do, right? So, I need to eliminate, I have 3 equations, this and this, I need to eliminate I1 and I2, right. Okay. So, from 2 what I have that I2 of S can be written as, so if I just write this equivalently as I2 times 1 over S C2 plus R2, right. So, I2 of S would be VC1 divided by this entire thing. So, this would be S C2 over 1 plus R2 S C2 times this one VC1 of S. So, all this will be S. Okay. So, now I have eliminated this from here. So, I know I2 in terms of VC1. Okay. So, we have eliminated I2 from equation 2 and okay, from equation 3 what we have is I1 is VC1 times C1 of S, right, this goes here, plus I2 of S. Okay. So, this is VC1 times C1 of S plus what is I2 of S, this entire thing, S C2 1 plus S R2 C2 times Vc1 of S. So, I will call this 4. Okay. So, my equation 4, I eliminated I1. So, I1 could now be written in terms of Vc1, I2 can also be written in terms of Vc1 from this expression here, and so I can mix, or I can just put these guys here to get my final expression in the following form: Vc1 S over Vi of S is, okay, I just skip the computations, but they should be straightforward to do. S R2 C2 over S R1 C2 plus S square L C2 plus 1 plus S C1 R1 S square L C1, this multiplied by 1 plus S R2 C2. Right. So, all this is in the denominator, is multiplied here. Right. So, what have we done, right? Again, so first is write down the individual loop equations and try to eliminate each of the variables to get an expression which will give us the ratio of Vc1 by V1. Right. So, similarly, I could also compute the transfer function from V1 or Vi to Vc2. Right, nothing changed, right. So, all this, so instead of, if this is my Vc2, the voltage across my capacitor C2, I can equivalently then find my transfer function as this one, right. So, equivalently, so what is Vc2? Vc2 is 1 over S C2 times I2. Okay. So, you could do the remaining thing as an exercise to find out what is Vc2 by Vi, given that Vc2 can be written as an expression like this, right. It is just the same steps that we will follow. Okay. Okay. So, the last problem for today. So, again, to okay. So, in the last problem for today, we are required to find the transfer function x of S over E of S. So, what does this electromechanical system do, right? So, I have a E which generates a current here, this current results in a back EMF over here, and there is also a force which this system exerts on this one, right. So, what are the constitutive relations here, right. So, the back EMF EB is K dx by dt, okay, and the force is proportional to the current K2 times I, right, the force which is experienced by this mechanical system over here. So, we are required to find out what is the transfer function starting from this input E resulting in an output here. Okay. So, these are two subsystems, right. So, one is this electrical component and one is the mechanical component. So, let us analyze each of them individually. Okay, so the mechanical component for M here, which possibly this experiences a force in this direction like this. So, there is a K here, there is a K here, and there is a D here, right. Okay. So, well, I can directly write down the equations for this because I already know this, right. So, mx double dot plus dx dot plus k times x for the spring. So, you have two springs, that will be 2 kx, d is the damping and k are the spring constants. This guy would be equal to the force, and what is the force? The coupling between this mechanical system and this electrical systems comes via this current I, right. So, this is F times I. So, I can write down this as S square m plus S times d plus twice k x of S is, sorry, I just made a mistake here, this is k 2 times I. So, this would be k 2 times I of S. Okay, that's with this part here, over here. Okay. Now, the electrical part, right, I can write down this as equivalently in the S domain directly. So, I have 1 over Cs R here, S times L, and I have a E, and I have some, I will just draw a block here called the EB, right, or the back EMF. Okay, and this is the current I which I am interested in here. Okay, and let me call this current over here as I1, right. So, the first equation would say E is R I1 of S plus 1 over Cs I1 minus I. Okay. And the second expression would be I minus I1 1 over Cs plus S L times I, again plus EB is 0. Okay. So, okay, what is this EB? EB is K1 dx by dt. So, I could simply write this as K1 S x of S is 0. Okay. So, I have this equation relating x and I have these two equations relating the currents and the input voltage. So, I can just make use of these three equations to eliminate I1 and I, and ultimately find the transfer function x of S over E of S, right. And I will leave the steps for you, but they should be very straightforward, right. So, if take this equation, you can eliminate one of the current variables from here, one of the other current variables from here, and from here. So, here you can directly eliminate, possibly write I directly as something on x2, substitute that I over here. Here you could eliminate I1, you already know I in terms of x, do all the computations and thus get the equivalent expression. I will just leave the computations again for you as an exercise. So, these were some simple examples in of course of solving Laplace transforms, solving ordinary differential equations, and starting from a system configuration how to arrive at the equivalent transfer function, again via all the everything in the Laplacian domain. So, for future purposes what would be easier is to equivalently draw these circuits in this form, right. Then you just have to treat them just as impedances and then write the equations directly as linear equations. You might have done this in some of your circuits course, circuits or networks course. So, just a little recollect of that would help you write down the equations in a much compact and much easier way. Okay? Thank you.